Okay, so again, I'm kind of sleepy today, which means I'm going to probably fall asleep halfway through this lecture and not remember what I did. So I've given the attendance sheet out already, right? Yeah. You're going to give that to me and make sure I take it with me downstairs, right? And, oh yeah, geophysics. Today what we're going to do is talk a little bit about, we're going to follow on a little bit of what we were talking about last time, okay? Because I know this is almost a dead day. This is as close to a dead day as you're going to get. The holidays start in 2 days' time. Tomorrow's last day classes. We're not going to meet again until after Thanksgiving, all right? And when we do that, we're going to concentrate on the last part of this course, which is sequence stratigraphy. I'd like to start off a little bit by giving you an introduction as to how this is all derived, but rather than going to a lot of detail, which most of you are not going to remember, I thought instead what I'd do is just go over some of the things we talked about previously for the sequence lab, or the seismology lab that you had last week, okay? And give you some opportunity towards the end of the class if you have any questions in regards to the stuff that's due tomorrow to ask it at that point too. And I will be here until tonight, probably until around 8 o'clock or so. So if anybody has any questions in regards to their sections, now is the time to get me. I'm going to be printing off posters, so look around room 137, and while I'm printing there, I've got nothing better to do but to answer your questions. Although I probably will be asleep most of the time, okay? Just if I'm asleep, if my eyes are closed, I'm asleep. If my eyes are open, I'm probably still asleep too. You get the idea. Anyway, let's talk about what we did last time. We introduced the whole concept of seismology, and we talked about this whole resolution versus penetration issue. We talked about sonic logs, and then we talked about some techniques. We didn't talk about enough of it, in my humble opinion. So what I'm going to do is I'm going to go back over some of these things, add a little bit more stuff, give you a couple more formulas, nothing new, you've dealt with this before, and just give you an opportunity to ask any questions in regard to the seismology lab that you did on Thursday's class. Because showing you what to do and having you actually do it are two totally different things, okay? This was our introductory session in seismology, talking about how the idea that we can actually just use sound waves. Sound waves are really useful. They basically bounce off things, and if we have the technology where we can emit a certain wave and receive a certain wave and count how long it takes between the time we emit and receive it, we can determine an awful lot about, oh, I don't know, where the fish are, or what the bottom profiling looks like, or ultimately, if we tweak it just right, what the subsurface geology is all about. I cannot say this enough times though. We're not talking about physical geology. Everything you get here now requires interpretation. And whether you're a good geophysicist or a bad geophysicist is how you interpret the signals you're getting back, okay? It's always better to have a physical sample. And if you had the opportunity of getting a core every time someone drilled a well, it would be a far better world when you think about it in terms of geology. We also talked about how we can actually use marine surveys to more or less do vast areas over a very short period of time. This is an important consideration again, because if you're working in the petroleum industry, hydrogeology, or any industry that requires results, if you're looking over a large area, you need to be able to survey that large area within a very short period of time. And ultimately it's because you have to compete to buy the property to do the exploration. And if it takes you 5 years to survey the property, but you only have 3 years versus 3 years left on your license, then you're not going to be able to survey it effectively, you're not going to be able to do the whole thing, and you may miss something, okay? So ultimately you do this because there's a cost advantage. And then we talked about different survey lines too, and the fascinating thing about doing marine surveys is these things can be huge. I mean, we're talking about stuff that can resolve the bottom of the oceans over large areas. I'm going to show you a couple new techniques which we haven't had a chance to talk about, still relatively new techniques that build up a literal picture of what the seafloor looks like. It's incredible what you can determine if you put your mind to it. Now, let's start with those other seismic techniques, because, you know, I was going to tell you about marine and terrestrial techniques, but didn't have a chance to. Let's talk about some of the other things that are really kind of interesting. I did mention a couple of them. Let me show you how they all work. One of the most interesting types of techniques we have is something called side-scan sonar. Now, the term sonar, of course, is what is used as a means by which to measure distance, and sonar is what submarines use to determine where other submarines are and where the bottom is and where any obstacles are. But it's basically the same type of thing. It's a seismic technique that emits a ping, you hear it bounce back, and you can basically more or less measure how far things are away. Side-scan sonar is essentially directional looking seismology. What you do is you tow a fish behind a boat, so that line leads to the boat at the surface. This fish, and it's basically a torpedo-shaped object, has transmitters and receivers built into them. Now, instead of looking straight down, as most transmitters do, these things actually beam signals off to the side, hence the term side scan sonar. So what you're looking at here now is the beam swath path, okay, that comes off to the side. This is towed above the seafloor at a certain distance, depending upon what kind of sonar you're dealing with. All right, it might be 50 feet above the surface, might be 500 feet above the surface. What it does is it sends out these beams sideways, and by doing that, allows you to resolve what the seafloor is like. Now, the neat thing about this is that it uses a radar, a sonar technique. So assuming now that you have a pit on one side and maybe a rocky outcrop on the other side, the fish that you're towing through, okay, is coming towards you like this now. So you're looking at it in terms of the fins in this direction. One beam is going off in this, one beam is going off like this. The other beam is going off like this. There is a certain dead zone that you're not going to see anything. Right below the bottom of the fish, this interval through here, where the ship's path are, that will not have any image whatsoever. But off to the side, it will pick up whatever happens to be there, okay? So as you go through, move another pit over here, I guess. What will happen is, when you have the beam hitting on a surface that is favorable for reflections, you'll end up having more signal reflecting back in this direction, less signal from this side. If you wish, that's the bright spot. This is a shadow zone if you were thinking about light. For rocky crags and all, that's where the reflective surface is going to be coming from, and this side is going to be more in shadow. So basically, it's the same type of thing as you would do if you were looking sideways with a flashlight. The computer knows how to interpret those reflections and can build up a picture of the sea floor. And literally, because you're moving back and forth, position where the object is and give you its three-dimensional shape because of the constant pathways you have. So this is the type of image that you can get. These are actual side scan sonar images that people found on the bottom. And this is such a high resolution technique that you can recognize shipwrecks. I mean, this not only is a ship, but this is a twin-masted ship, and you can even see the shadow. This is a seismic shadow of the mass also reflecting backwards. So you can just imagine what kind of resolution you're going to get in terms of the bottom geology if there's such things around there, okay? And indeed there is. This is seafloor mapping. Now, you don't see very much from this view, because what you're looking at here are the various stripes. What they do is they put them all together, they cut out the dead zone between them, glue them together, and you get this pathway that you see here. What you're seeing is a little bit of a contrast image in terms of some issues. These little stripes you see along here, these things are normally associated with waves. And someone asked me this earlier about the large methodology you use. If you're going deep, with the resolution being what it is for deep seismic, you're not going to see this type of movement. But if you're in a boat where the waves are 30 feet high and the bottom only has this much difference between it, every time you have a lift up when you're going up the crest and sinking down the trough, you are going to see some disturbances along the surface. Still, it's sufficient to go from this into this. It's seafloor mapping. In this case, what they've been able to identify are bare rock, where there's coarse sand, mud. You can actually, in some cases, see ripple marks. You can see directional currents. You can see all manner of stuff. It really is quite cool. And there is practical applications to this type of seismology. What you're looking at here are iceberg scours off the coast of Newfoundland. Now, I actually have some insight on this because I was around I did my master's degree in Newfoundland, and I was around at the time that they were trying to develop the offshore oil industry in this area. It's now one of the major exploration areas in North America for production of oil and natural gas. But it's also an area known as Iceberg Alley. The Titanic sank in this area because it hit an iceberg. What you're looking at here are scour marks where icebergs were grinding along the bottom. They're directional because the icebergs are moving, right? So they're moving in that direction. They are big enough that they're touching down on the bottom. At least that's what the inference is on this. And by the way, the water in this area is between 200 and 1,000 feet deep. It's deep. So if you've got an iceberg these things are big enough that it could be 1,000 feet below the surface dragging the bottom. Now you're about to produce oil at this location here. How do you get the oil from below the surface to the shoreline? How do we do it here? Pipelines. Do you put a pipeline here? All right. These scours, in some cases, are 30 feet deep. The question was, are they active scours or are they remnants from when sea level was lower? That was the big question at the time. As it turns out, some of these things are active, some of them are not. So they actually had to make a decision in terms of how to get the oil off from below the surface here to the shoreline. They don't have pipelines. They actually have a production platform where they put oil tankers, load them up at the site, and then take the tankers back. But they still have to worry about icebergs. In this area, one of the largest structures that humans have ever built is on the seafloor here. It's an incredible story when they built this thing. It basically is a platform where they have a production platform on it, and surrounding it is a huge concrete curtain that is designed to deflect most small-scale icebergs. The biggest ones are still a threat. You know what they do for these things? Have you ever seen the program on this stuff? They literally tow these icebergs. I've seen them do this once. It is incredible. Okay, so here's an iceberg that might look like this, right? The tow boats, the standard size pilot boats you see around here in terms of scale are like this. They take a steel cable about this thick, they go around it, lasso it, and then they just tow it full out. One of these cables broke once. When they were towing it, took the entire superstructure of the cabin off. There was so much tension in this thing when it finally went, it just cut it right through like butter. People on board that ship said they knew they were in trouble when they heard this really god-awful noise, and they all ducked. That's the only thing that saved it. Nobody got hurt in this whole thing, but they should have been all decapitated. Cool stuff, all done by Seismic sonar. And then we have the really cool stuff. Now this is fairly new, relatively speaking. Gloria, and I'm not sure what this actually stands for, it was some god-awful name that was just shortened to Gloria, was developed by a British research team. It is essentially a high-tech, ultra-large swath side-scan sonar. It was done in the 1980s to start with, and it was designed to do deep water side-scan profiling of the seafloors. It can only be done in deep water. It cannot be done on the shelf. So we're talking about open water stuff, okay? That's the technical stuff for Gloria. I think I mentioned to you that it was like 60 feet long. When we were talking about this briefly, I lied. It's only 8 meters long, so that's about 30 feet long. But it weighs 2 tons. That's metric tons. So this is the type of thing that cannot be towed behind normal boats, especially since you have to have the thing sitting at around 500 feet below water. That means a lot of cable, a lot of towing strength to pull this thing. Here's the incredible thing. It can survey 18,000 square kilometers per day. Let that sink in. 18,000 square kilometers per day. This thing is incredible in terms of what it can do. It's still side-scan sonar, so it still does the same thing. But now we're talking about swaths that are on the order of 100 kilometers wide. But with the same problem we had with resolution versus penetration, this is a resolution versus swath side. The resolution now is 50 meters. That's 150 feet. So anything smaller than 150 feet, you're not going to see on this. But what you see still revolutionized our idea of what's going on the slope and on the abyssal plain. These are actual side-scan sonar images. They don't look very good because they're not really jazzed up very much. There's the paths, which you're looking at here, that looks very much like the Mississippi River, is about the size of the Mississippi River, but it's in water probably 1,500 feet deep. It's an underwater channel system, all right? But that's the best resolution you're going to get on this. You can see submarine fans, you can see underwater volcanoes, you can see fracture zones associated with tectonics. Anything that's a large-scale stuff, this type of thing can actually reveal. And by the way, if you're wondering who does this type of stuff, governments do. This glorious survey, the first glorious survey was done for the United States government. Basically what they did was they towed it all the way around the continental United States, Alaska, and Hawaii, just to more or less map out what was on the seafloor. Why would they do that? Several reasons I can think of. What's one of them? Resources. All right? If you start seeing things that might be oil, if you start seeing some fracture zones, there might be some oil associated with it. You learn where your resources are. But remember, this is not necessarily within your economic zone. But if you find it first and claim it first, you can still more or less sit on it. What's another reason? Why was the United States Navy involved in this? Well, not to find subs, you're not going to find a sub, but it's not a bad idea to find out where the rocks are, because we haven't mapped out the entire seafloor yet, okay? So mapping out the entire continental area is not a bad idea to find out where there are places where you can hide some subs. That wasn't sufficient for the organization that developed Gloria, because the resolution issue was such that you couldn't see like detailed stuff, so they developed a smaller version, Toby, and smaller means smaller swath size, but better resolution, okay? So Toby is just a smaller version of this, and that's the type of thing you could just kind of take off of like a normal research vessel. It does the same type of thing though, okay? That doesn't look as pretty. It's towed behind. It is also capable of shallow penetration down to about 70 meters. And here what you see in terms of things is much better resolution. It's towed closer to the seafloor. Remember that channel I showed you before? There's a close-up of what the channel looks like. And this is cool because you can see the channel walls. You can actually see an underwater levee system. And this is the top of a slump scarp. This is, of course, the source of where things like turbidites are going to originate. So this type of side-scan sonar is such that you can look at smaller scale things, but still much more larger things that we would normally see, okay? So you're probably looking, that might be 150 meters across, perhaps, and you can see the detail, including some of the structure in there as well, okay? Now notice 2 meters resolution rather than 50 meters resolution. Okay, so I just want to fill in a gap there, and what we're going to do is we're going to fill in some more gaps in terms of what we did previously. So we're going to talk a little bit more about sonic logs. These are also known as acoustic logs, by the way. I didn't tell you that earlier. We're going to link this through what we did previously. We're going to talk about the synthetic seismics. Again, just take you through the whole thing again, and then talk a little bit about seismic interpretations. And the last thing we're going to do today is talk about Peter Vail, and this is our introduction to sequence stratigraphy, which we'll get into after the break. Okay, so I'm just going to tell you a little bit about who he is, why he's important, and this will tie in things for those of you who've heard of the Vail curve before. This is the guy who ultimately is responsible for it. All right, so we talked about sonic logs. If you recall, sonic logs or acoustic logs are a type of sound that we drag with everything else, and this is showing you as if it were a separate sound. This would be a compartment was built in with one of those large composite things that the oil industry does. What it does is more or less determine two-way travel time within rocks. So basically what it's doing is measuring the response of rocks and linking it to the stratigraphy that we know. This is important because what it allows us to do now is say, if you're in the Capello Formation, the Capello Formation has this velocity of waves going through it. That's one of the key ingredients that we need to know for interpreting seismic logs later, or seismic profiles a little bit later on, okay? I also mentioned to you that this is important enough that we have to really have a lot of detailed information, and what this table is here, and you don't have to worry about it, it'll be online a little bit later on if you are interested. It's showing you a couple things. What the density of rocks are, because density is one of the important components that are going to be controlling the speed at which seismic waves go through. And somebody somewhere literally determined that a sandstone has a density that ranges from 1.61 to 2.76 and has an average of 2.35. One of the issues always with interpretation of abstract data like this is you have to put a number in. And when you're first doing this, if you don't really know what the actual characteristics are of the rocks, you put in the average number. This is something hydrologists do all the time when they're doing hydraulic conductivity. You put the average number in. That seldom works 100%, which is why we still do tests. if you want to actually get a really good handle on groundwater flow, you have to take a physical sample, do measurements for the permeability, porosity, and then plug those numbers into any calculations you're doing. Always remembering, of course, that just happens to be the porosity and permeability of the sample you collected. It could change laterally dramatically. If you don't have those data, take it off a chart. Engineers love charts like this. Also remember, there's also the other thing you have to take into account, that the deeper you go, and this is especially true if you're dealing with oil and gas, because we're talking about things that might be in the subsurface, the deeper you go, the more density is going to change because it's getting more compressed. Confining pressure, if you increase the confining pressure, will increase the apparent density of the rocks you're dealing with. All with the exception of salt. Salt's fairly consistent in terms of its properties, which is why it's got this nice red thing here. Everything else kind of increases as you go down into deeper levels. And it's ultimately this that's going to allow us to actually start interpreting diagrams like this. Now, these are some pretty cleaned up diagrams, so everybody should immediately be able to see, number one, an anticline, a syncline, another anticline. Can you also see the unconformity? Can you also start to see some of the low angle truncations that indicate there's probably a second unconformity or possibly some sort of a down cutting surface? All right. After a while, you get into it. There's the folds, there's the major unconformity, and then up and through here is another one. Actually, there might be another one in through here as well. And this, not sure what that is, some sort of slump structure possibly. The point is, when you get your eye into this, you're going to start seeing changes laterally. And the best way of doing that, of course, is to look sideways. But these reflections, what you're looking at here, is the contrast between contacts. And remember, if you're going to get a nice sharp contrast like this, there's got to be some really significant difference between the property of the rocks here and there. And you also have to have a certain resolution dependent upon what the frequency was. If this bed here were not sharp enough or not thick enough, it would not appear as a consistent bed here, okay? So resolution, penetration, reflectivity, strength are all dependent upon the properties of the rocks, and those properties are going to vary from one layer to another. Now that takes us to these formulas. You may or may not recognize these formulas. This was one of the first things we did on the calculation. I just gave you a bunch of numbers. Basically, it was a fill-in lab as we were doing the transition from Connor's stuff to my stuff. But if you recall, we talked about the acoustic impedance. This ultimately is what's going to control the intensity of the reflections you see in these seismic profiles. Okay? So, the acoustic impedance is defined as the velocity of the seismic wave, that's what the sonic log is going to tell you, times the rock density, which is what you're going to get from a chart or what you're going to physically measure. And by the way, it is possible to measure the density of the log, of the rocks, through a log as well. They're called density logs. Or you can even take a physical sample. There are means by which you can actually take a sample of the rock off the side of the well as you're pulling the sonde through. Like I said, they can develop all sorts of technology if it's going to help out and all. All right, so acoustic impedance is simple. Velocity times density. And that will control more or less what's going to happen with these contacts through here. The reflection coefficient, this is again things that you calculated on that exercise I gave you a long time ago now, is just simply the differences between the acoustic impedances of each of those different layers. All right, so that tells you how intense the reflectivity is going to be. And ultimately what this math is telling you is that if you want to see a surface, there better be some major differences between the rocks on either side of the surface, either density or velocity. All right, and that's all that this is about. If you don't have those differences, if there's no difference in acoustic impedance, you're not going to see a contact, even though it may be a sharp contact between geology. And remember again, the density of most siliciclastic rocks is going to be fairly consistent. Shale, sandstone, all have about the density of quartz, which is about 2.65. The limestones, the dolostones, and hydrites, those are going to be different. But those may not be the rocks that you happen to be dealing with, okay? Just the way it is. There are good places to explore, easy things to interpret, more difficult places. And guess, if you're in an area where there's difficult stuff, the best geophysicists are going to be the ones that can look at these very subtle differences and still find enough stuff to determine where to drill. All right, and ultimately we talked about how we went from these different components. We have a sonic log, we have a density log, and then we put it through a computer program, start compiling it all together, and it gives us these squiggly little lines. And remember, it's these squiggly little lines that are telling us that there are differences, either positive changes or negative changes as you go down hole. This synthetic seismic that you see here allows us to link this pattern with what these large-scale seismic profiles are showing us around the countryside. All right, and we talked about, again, this one here just allows us to go from here to there and then ultimately to give you this. I didn't really explain this all that well when we were doing it initially. What you're looking at here, this is the seismic pattern, okay? The seismic, synthetic seismic you're going to get is going to more or less give you one series of curves showing you positive, negative changes. The real trick is to take this and now compare it with something that is going to show you lateral changes. So here you can see this contact is actually dipping a little bit, this one's dipping a little bit, this one is pinching out more or less on these sides. So what the synthetic allows you to do is to link it to what the actual regional seismic sections are showing you, and then from there you can see how things change laterally. And ultimately you get things that look like this. Now again, I have to warn you, if you work in the oil industry these days, they are normally color coding on a regular basis. Blue, red, white. Okay, the white is showing you places where there's no real differences. Blue is positive and red is negative, I think. If I was less tired, I would know that. So this is the norm you see here. We can't give you these in this lab because we don't have the means by which to photocopy color on large-scale format. Okay, we just don't have that ability. So we just do the black and white component. When you get into this and you start looking at it, you'll be able to make all manner of observations. For example, this is a classic North Sea graben. Basically, one side has been uplifted or down dropped, and what you're looking at is the sediment fill that is filled in this graben, and we're talking like several hundred meters worth of sediment. Obviously, this is a place you want to drill in, because if any of these things have reservoir characteristics that are such that they can trap oil or gas, you drill into them. You got a big, thick sequence of sediment through here. Great place to go look. Beautiful fault system, which you can see in terms of how it disrupts things. And in fact, there's a couple of faults probably side by side in this area. When you get good at this, you can trace the faults throughout an entire sequence. And of course, all you need is just practice and patience to be able to be good at doing this. All right, so strong reflectors. I get a warning. You have to worry about interference. For example, this looks kind of complex here in the middle, but what you're looking at basically are multiples. In other words, these are reflections that the computer cannot filter out. And this does happen. It's a resonance type of phenomenon where certain waves get reinforced and get a little bit stronger. And you don't want the computer to be basically filtering out everything, because if it does, it might filter out something that is really important. So you leave these in, and a good geophysicist would be able to recognize these as multiples. I am not a good geophysicist, so I don't know how you can more or less say that is a multiple there, but that may not be. The fact that they cut through one another like this, I know, has some significance in this, but this is one of those things that you just have to have a lot of experience and know the area to be able to determine what's real and what may not be real. And then we started playing the game, okay? This is what it comes down to. You need some practice, so I gave you some examples to do in the lab. Most of the ones you got to do to take home with you were relatively straightforward. So by now, everybody here should be able to spot the anticline structure, and can you see the two faults? All right. Anybody not see two faults associated with the anticline? Even from there, you should be able to see them. Classic ones. Through here, through there. In fact, this one here has literally pulled things up. Or actually, probably what's happened is these things are splayed off like that, and that block has just fallen down and rotated a little bit in that direction. Sometimes they're easy, sometimes not so easy. And again, I'm going to just show this to you because you can see some faults. Now, that's identified as an unconformity. If you get really good truncations, and we saw some of these in the examples I gave you, where there were clearly some rocks that were tilted like this or folded below, and you see the whole top being planed off. Those are easy to identify because they're angular. And angular unconformity is no problem whatsoever. How do you identify a disconformity? Anyone? Yep. No vertical angular differences at all. You can do a nonconformity easily. A nonconformity where you have sedimentary rocks sitting on top of crystalline rocks, you'll see the contact vary dramatically because sedimentary rocks will give you a horizontal structure. What kind of structure do you get if it's a crystalline rock? What happens? All right, you get things all being kind of convoluted. There's no lateral continuity. If you have sedimentary rocks sitting on top of sedimentary rocks with a disconformity between them, the only way that you'll be able to tell that there is a disconformity is to know that there's a disconformity there before you start looking for it. In other words, in the same way that someone can come along and call that the Cretaceous, this the Jurassic, this an unconformity, is because they have wells through here. They've got the stratigraphy sorted out. They took that synthetic seismic line and they saw what the characteristic was of the unconformity and were able to match it and laterally go along it. So in other words, you can find an unconformity easily. You can find disconformity easily, as long as you know what the seismic character is of it before you start going looking for it. These, incidentally, is what we would call reflectors A, reflector B, reflector C, before we knew what reflector A, B, and C actually were. All right? So if you're doing wildcat stuff, if you're going to an area where it's never been drilled before, you do the seismic lines, you look for some of these little bumpy bits that might be a good place where you might have a reservoir, you drill through it. If you're lucky, you get oil. If you get oil in that area and you want to find more oil in the region, you do your well, you start pulling out samples, you start identifying what the rocks are, and from that you develop your synthetic seismic so that you can trace it out and go laterally. If you know which formation has the oil in it, you go looking for the formation in other areas. And ultimately what you really want to do is to be able to build up something that looks like this. This is a 3D seismic model of the subsurface. This is what you're going to be doing in the last exercise in this class, although not quite as complex as this. What you've got are seismic lines going this direction and throughout this entire region through here. You can't even see the seismic lines. But what you can do now is you can go down to a certain interval. You can take a slice, they're called time slices. Basically, time slices are equivalent to depth slices. If you go down 3 seconds, two-way travel time, that will represent a certain surface below maybe 1,500 feet. And what this will show you is the characteristic of the rocks over a 3D fashion. In other words, this is showing you things like faults. This is showing you things like some sort of, I don't know if that's a basin or a domal structure. This is what the section looks like with all sorts of thrust faults coming in through here. This is something now that is routinely being done. And here's where I wish I had access to what some of these training organizations do. I took a short course. Connors and I both took short courses on geophysics about 3 years ago, I guess now. He did one that was on magnetics, gravity, etc., because that's what he was teaching. I did one on this. The company that put it on was a combination of BP and BHP. BHP, big Australian mining company, also has a big petroleum component as well. They had seismic lines from this one area that we put together. We literally went along, put them together, and came up with the most amazing three-dimensional models. I asked if I could take those away and use them for teaching. They were immediately confiscated from me. No. All right? That's the problem. Oh, we have plenty of seismic lines. We have people giving us stuff all the time. But the problem is, we don't have anything that gives you a really good interpretation. So, much the same way as I had to make up these things for you guys, I had to make up my own seismic lines so that when you do this three-dimensional characterization, you're going to be able to get something that's going to be interpretable. It's not going to look like this, obviously, but it's going to come pretty close in some cases. All right? You got a lot to look forward to in the last couple weeks of this class. All right, now with that, oh, good timing, actually. Let's introduce sequence stratigraphy in terms of a short history. This is just the history. I want to introduce the person who's responsible for this, give you a little bit of background information about him, and then we'll talk about the specifics after the Thanksgiving break, okay? The concept is sequence stratigraphy. You've had stratigraphy before. You know there's a zillion types of stratigraphy. There's biostratigraphy, there's lithostratigraphy, there's chronostratigraphy, there's stratigraphy up the wazoo. Sequence stratigraphy is the stratigraphy that is done on the basis of seismic profiles, but not simply a matter of correlating reflectors to reflectors. This is much larger scale stuff. This is more or less correlating systems tracks from one place to another. It has worldwide significance, perhaps too much worldwide significance. This is the person who's responsible for it. This is Peter Vail. Peter Vail used to work for Exxon. When he was in Exxon, he's a geophysicist, and he was very insightful. He realized that when you are looking at seismic lines, not only are you able to correlate rocks from one place to another, but you can also correlate things like unconformities. And unconformities, especially in the offshore regions, are associated with sea level low stands. If you think about it, if sea level were to drop 300 feet, as it did 18,000 years ago, you're going to have all of the beach sedimentation moving well offshore. Around here was about 80 miles south of where it is today. What happens to the current beach? What happens to the shelf that is now exposed? What's going to happen there? What happens? Trees grow on it, rivers flow over top of it. You're familiar with the concept of base level, I hope, right? Base level is the level to which rivers will flow, and it's dependent upon the level at which rivers flow into. Base level right now, for the rivers that flow into the Gulf of Mexico, is determined at where sea level is. If you drop sea level by 300 feet, you drop base level. And that result is all the rivers that are slowly just flowing nicely into the Gulf of Mexico now, all of a sudden become raging canyons because they're capable of eroding significantly downwards. That's why Mobile Bay is here. If you were here 18,000 years ago and stood where Mobile is today, you'd be looking down into a chasm about 150 feet deep. At the bottom of it, which would probably be a river that's flowing fairly extensively. That's why we have cliffs on the other side of Mobile Bay. It's because it's an incised river valley. When sea level comes back up, what happens to base level? Base level shifts back up and the whole thing gets filled in with new sediment. So the sediment is shifting according to where sea level is going, and as sea level drops, you expose stuff that had been previously deposited, eroding it downwards, forming unconformities. There's surfaces that can be resolved through seismic analysis. All you have to do is identify which surfaces are erosional and which ones are associated with deposition. Vail knew that. Moreover, he worked at an oil company and had access to seismic lines all around the country and all around the world. Now think about this. If you can look at a seismic line and see how sea level has fallen and risen, if you can do it all around a country, if you can do it all around the world, if you can link times when all of the shelf areas were being eroded all around the world, what does that tell you? There was a worldwide sea level change. If there's only some places where you see these surfaces but not around the world, it's a regional sea level change. That's the one thing we've never been able to do. You cannot go to rocks anywhere and pull out the world curve from the regional curve. Even today, there are parts of the world where sea level is falling because of local disturbances. Sea level is falling in parts of the Mississippi Delta right now because we're dumping more sediment into it. Right? Our definition of sea level is where sea level is. If you add sediment into the shoreline, sea level is effectively falling. It's called a relative sea level drop. In fact, the whole concept of relative versus eustatic was based upon the work that was done here. You can pull out the regional variations from the worldwide variations. Finally, we have a means by which to look for that worldwide sea level curve. And Vail knew it. Moreover, he was working in an area where he had a lot of people who could work with him. He had teams. They sat on this stuff and started doing it and doing it and doing it and doing it. And Exxon loved it because if you think about it, if you know when sea level drops, what happens to all the shoreward sediments? Where does it all end up going? Offshore. If you could figure out how sea level was changing around the world, and then you went to a new area for exploring, and knew the age of the rocks you were dealing with, you'd have a real competitive advantage over everybody else in terms of where to look for big, thick piles of sediment. And there's no limit to how far back in time you can go with this eustatic sea level curve. As long as you've got the seismic lines, you can go back, all the way back to the start of the Paleozoic, or earlier. Although going earlier probably is not that practical, all right? Cool stuff. He started doing this in the 70s, and they were churning out all this information, and Exxon was taking advantage of it. But then they started to more or less go to the next phase of things, which is to publish it, to actually talk about it. And that's when all academics all around the world started getting excited about this, okay? All right, so 1960s, Exxon, and now he ended up, I'll give you his history in Vail. He retired from Exxon, let's see, must have been in, I guess, late 1980s, I guess. Went to work at Rice University, emeritus professor. Okay, he just more or less walked in any university he wanted to go into, and started teaching short courses. I actually had a short course with him in Australia. It was incredible. He's a very nice guy. As I said, he's trained so many people now. These people that used to work at Exxon now have academic positions around the world. He's responsible basically for a new discipline in geology, which is pretty darn cool. But there's a problem. And there's always been a problem with this. At least there was. When this stuff first came out, and I'll go right to that. That stuff that was before, it was just talking about Vail. When this first came out, this is the Vail curve. There was a problem. They published it and they said, here's how sea level has changed over time. But researchers could not actually go in there and resolve it or determine it, because Vail's information was based upon more or less classified seismic lines from Exxon. So he would say sea level was doing this in the Cambrian, the Ordovician and all, and people would say, well, how do you know? And he said, well, I've got the data. And they said, well, where's the data? I can't show it to you. This is a problem. And in fact, this is where I got involved in. My PhD was based upon stuff that was going on up in here. And all around the world, this was starting to be a real issue, because there were times when our work showed sea level to be rising at a time when sea level was falling, according to the Vail curve. And to this day, there are still problems linking this to what was actually happening around the world. Okay, so there are still issues with that. But now that we understand how it works, we're filling in a lot of these gaps that were there originally, and now we're getting better and better at doing it. So we have this idea of how sea level has changed over the world as a whole. Ultimately, this is what sequence stratigraphy has allowed us to do. You're not going to be doing this. If you work for an oil company, you're not going to be going in there and resolving sea level change. They don't care. What they want to know is, if you're looking at rocks that are Permian in age, at a time when sea level was a little bit on the low side, where is the most likely place that you're going to find sediments that accumulated in the right areas, where there was marine accumulation of material, got that organic stuff, where the source rocks were, where the traps could be, etc. So the Vail curve is great for academics, but it still has applications in the petroleum industry too, which is not necessarily going to see eye to eye. All right, and this is, again, just to introduce this, because we'll come back and talk about this a little bit later on. This is the sequence stratigraphy component of things. This is the actual interpreted curve. You're going to start seeing little bumps, different scales of things. And have you talked about first order, second order, third order, fourth order, fifth order changes in sea level? All right, you may or may not have. If not, we'll go over just briefly and all. They're controlled by different components, okay? First and second order ones are tectonic. Third, fourth, fifth, and now the sixth order changes are eustatic, associated with ultimately Milankovitch cycles and stuff. We'll go into this if it's over your head right now, okay? All right, and here's the reason why. This is the important thing. This is why we're talking about it now. When sea level rises and falls, you're going to start seeing shifts in where sediment's going to be deposited, okay? So when you have sea level drop to here, everything gets deposited over this area. This all gets exposed. When it rises back up, it shifts all backwards. That's the cool thing. All right, now with that, we're going to call it quits now. A reminder, tomorrow by 5 p.m., I want all your stuff from the previous lab. I want all your stuff from the lab that we had on Thursday. That means sequence stratigraphy interpretations. I've already got one of those. I want to see your SP logs again. I want to see your gamma rays. Those, if you modified them, I will give you a modified grade on them. I want to see your isopac maps. I want to see at least one top of formation map. I want your fence post diagrams. Everything by 5 p.m. tomorrow. I will get them marked as quickly as I can. Given the extent of these things, you may not get them back for a while, though, okay? You may not get them back until the latter part of the course. Yeah?
You want the isobac mass on the thing, put on a piece of paper?
Whatever you want to do. All right? Remember what the purpose of this whole thing is. We don't meet on Wednesday. We don't meet on Thursday. Ha-ha! Thanksgiving. Don't overdose on turkey. Next week, sequence stratigraphy for real, including more jargon than you thought was possible outside of a paleontology class. Know some of these things, because when you go for an interview with an oil company, they're going to ask you this stuff just to see if you know anything about it. Okay? With that, we'll see you later. Have a good holiday. And if you're interested in getting extra bonus points for this course, at least for my part, sign-up sheet outside my office. The mineral poster show is tomorrow as well. Everybody's welcome to come and harass the students. Remember, they harassed you last year. Payback time. Lights coming on. Thank you.